So, to get started right off the bat, we're going to, start with training like a 1.3 billion parameter model on just a single CS2. And I'll kind of walk you through how that looks today on an ALCF machine on the setup. So as you can see, I SSH'd in, nothing too specific or nothing too different than how anyone else to access any ANL setup. As we discussed yesterday, we need to set up a Python environment. This one's already pre-set up. This is with the software release that is on ALCF. Anyone can do this based on once you have access. If you're curious to know where these packages live, they all live under cd opt. My bad. If you look under wheels, you will see all the wheels exist here. And if you follow the instructions from the website, you'll be good to go, essentially. So I basically installed these wheels into this environment. I then, as discussed yesterday, cloned the model zoo that we're all familiar with. And specifically here, I'm going to be running the GPT-3 model. Can everyone see the screen large enough, or do we want me to make it bigger or anything like that? Is it clear to everyone?
So I can see it pretty well, but I'm have a large external monitor.
Okay, yeah, that's I just want to check in case if any of this looks too small for people, I can make it bigger. Okay, don't see anything, so okay, I'm going to assume everyone can see it. If not,
I think it looks good.
Looks good. Thanks, Morley. So this is just our vanilla version of the model zoo. I've prepared. There are a few configs that comes with it. So you see, so GPT-3 XL is essentially our 1.3 billion, but we have YAML files available up to 20 billion. The default and the GPT-3 are essentially the same thing here that I've just copied for this case. And to get started, I'll kind of walk through what the command would look like, and then we can go through what it's actually doing, right? So for, if you remember from yesterday's both Bill's talk and Richard's talk, we're going to be using PyTorch, we're going to be using weight streaming. In this specific case, I'm going to be running the GPT-3 1.3 billion on the OWT dataset for about 200 steps. For context, that's roughly 50 million tokens or so is what we're going to be training here. And so here I specify the configs is the default YAML. I'm saying I want to run train. I'm just specifying a model directory where all the artifacts, your checkpoints and things will be saved. You do have what we call the mount directories, which is where your data is stored or where some of your other code is stored. And then Python parts again is where your model zoo code is, so we can access it. And then you specify a compile directory if you need to. You don't necessarily have to, but it's often a good idea to kind of keep yours separate from others. And that's basically it. Once I get this running, I'll walk through what some of the other tools that we have with this. But it usually takes a few minutes to get going, and then I'll show you some of our other tools that were mentioned yesterday. In the meantime, I'm just going to log in through another node here, just so I have another terminal. Right, logging into the first node again. Right, so yesterday, I think Bill mentioned that there's a tool called CSETL. So I started to show you what that looks like. So you can do CSETL get jobs, and this will show you a history of all the jobs that have been run so far. Now, specifically, if you want to see what's running, you can do jobs and run. You can see currently nothing has been queued up yet on the system, mainly because this job is still running on the user node. It's just starting the compile process. So some parts of it happens on the user node, and then a large part of it happens on the appliance. So we're going to quickly just compile this model and then proceed. Now, if you're going to just extend your run or retrain a model, we do have mechanisms where we cache the results of the compile, so you don't have to go through the entire compile process every time. So depending on the level of change, the compile could be quite short, in the orders of seconds as well. So as you can see here now, we see that we have a job running. Currently, if I adjust this a bit, you can see that there's no systems allocated to it because it's doing a compile job. You can compile without using the cluster, without using actual CS2s. It's done without needing to occupy the CS2s, but it will use some resources from the appliance. And as you can see, the compile job is complete. And now it's kicked off an execution job, right? And if you see here, it says, okay, you've kicked off a CS2 job, and we're using the second of the two CS2s, we're using one CS2 here. We do also have integrations with Grafana and things like that. I won't be going too much into detail here, but it's covered in our extensive documentation that we shared. So for those of you familiar with it, you can kind of see what jobs are running, what the status of things are, what is there any errors, hardware issues, things like that. It's usually more aligned for your sysadmins and things, but I do know there are researchers who are curious about it, especially if you're looking to see what the utilization of things are and things like that. And as you can see on the left-hand side, we've kicked off the job. It's going to be running on one system fairly soon. Once we start seeing some losses, I'll kick off a TensorBoard, or I can probably spin that up in the meantime while we wait for it. So, just your normal TensorBoard that you're familiar with. For those of you curious how to do it across the thing, at the very beginning, when I SSH'd, I do a port forwarding. So that is something you'll need to do when you're logging in, so you can see it on your local computer. And then, as you can see, nothing's been done here yet because it's still transferring the weights. So it's training from scratch here. There's no initial checkpoint provided. So it's generating the weights and then transferring it onto the appliance. So normally this process is a function of how big your model is. We do have ways to improve the performance based on the cluster size you have and resources available and things like that as well. As you can see, this doesn't take too long. We're talking orders of minutes for a 1.3 billion parameter model. Even as you get bigger to 30 billion, 100 billion, it's still very much in the orders of minutes. But most of these things happen. So we're now done sending the initial weights. Once the weights have been sent, we'll start seeing the training results soon. We do provide a way for you to see on the terminal as well the losses being returned, as well as if need be other metrics that you're calculating. Since we're training here, I'm mainly only going to be showing the losses. And then once those losses start populating, I'll switch over to the TensorBoard and we can take a look there as well. So while we wait for it to get started, one thing to keep in mind, we do have a scheduler underneath here, which is built on Kubernetes. So the scheduler goes through Kubernetes. So even if you queue up many jobs, let's say you have access system to both the systems, but you have 5 jobs, 10 jobs, you can queue them up so that you can queue them up and leave and then come back the next day to have all your jobs completed. You don't have to be there to launch them one by one. The orchestrator will handle it all for you. Any questions so far? We're waiting for it to start populating. So we will be seeing the losses every 10 steps or so. And yeah, as we can see now, we're starting to see the first set of losses show up. Let's run 10 steps, again, training from scratch on the OWT data set. So, and we should be seeing quicks pretty soon on the TensorBoard as well. TensorBoard sometimes tends to lag compared to our runs, mainly because TensorBoard updates only every 30 seconds or so. So it's important to keep in mind, but for longer runs, you would be able to see almost in real time the performance. As you can see, we're making further progress. We'll run for about 200 steps in total here. Saugat asks a question: do we need to go through this enterprise every time, even if I just want to retrain the model without recompiling? If you're retraining the model for additional set of steps, you would go through this process. The compile time would, if you're retraining the same model, let's say at a different checkpoint, or you're just continuing your training, your compile would be much shorter, but you would still need to transfer the weights over, and then the actual training takes place. So as you can see here, the TensorBoard run is started. That. And the loss is starting to go through. Later on, as we do some of our other demos, we'll be able to see some of the performance differences as well. So this is just getting started. Now, if depending on whatever model you're running, sometimes you want to track other metrics and things like that. Those can also be captured here as well as on the TensorBoard. In this specific case, we're only looking at the losses. But you can add other summaries and things like that as well to see how the behavior of your network is over the longer training runs. Go back here. Bigger. See it. The loss is trying to converge. Obviously, we're doing a very tiny run here to get this to full convergence, so we won't see that. But the loss curve is showing the right properties. Another thing to keep in mind is we do support also both. We do most of these runs in mixed precision, and we do support both your traditional FP16 as well as your bfloat16 operations as well. So any of you are curious why the numbers seem aligned so well, it's because they're being returned back as a bfloat 16. Right. And that's essentially the full training run. If we give this a second, it will update on its own or refresh. Like I mentioned, TensorBoard tends to lag a little bit just because it only updates every 30 seconds or so. But as you can see, it's gone to the 200 now. So yeah, this is just like the very first demo, just to show what getting started looks like on the system, right? This is taking a publicly available data set, taking our model zoo code, our Python wheels, and just getting familiarized with the system. I see Alfred has a question. So we're not covering what Bill, I see Richard has answered. We're not covering what Bill showed for those curious. We're going into further detail on how do you actually run things on our system. How long does it take to get going and things like that, and how easy it is to use. Now, before we continue, I thought I'll quickly walk through what the YAML looks like. So as you can see here, we specify our data directory here from the OWT. This is uploaded already on the ALCF cluster on the common shared storage that Bill and Murli mentioned yesterday. We're running with 2048 sequence length. You can it's a similar setup for eval. The model here again using a fixed vocab size, similar hidden size, and these are the various parameters that you can change and tune to meet your needs. And then similarly, as you can see, as I mentioned, we're doing mixed precision. We have an using RNW for our optimizer and our learning rate schedule. And then, as I mentioned, we're doing a total of 200 steps. The log steps, we're printing the logs every 10 steps, and similarly on the thing. And that's about it, right? So that's all this config has. It just describes what the model is doing. You can obviously play around with this, change it to fit into your model's needs. And as Richard mentioned yesterday, you could also obviously make changes to the model itself to fit your needs, but we wouldn't be going too much into that here. So this is just like a default run, right? But this one only used one CS2. So the next thing we're going to be trying is, well, how do you use two CS2s, right? And again, the command looks pretty much the same. It's, we have a run.py, it's the same GPT-3 model. I have a separate config here called toSystems.yaml. It's a different model directory, everything. And then I specify num_csx equal is 2. Now, for those curious, what's the difference between the YAMLs? We can quickly go over that. So right, so the only difference you see is that I've changed the batch size. So why have I changed the batch size? At the current release that is on the system, the batch size specified is per system. So to maintain the same batch size, I just reduced it by half since we're going to be running on 2 systems, but that's pretty much the only change. And then I add the num_csx equal to 2. Right, and that's pretty much all that's needed. And then when you run it, we'll now see that it'll use 2 systems. Once it gets going, I'll again similarly show the CSETL get jobs. So you can see that it's using both systems, and then we can go over to the TensorBoard and we'll see a linear scaling and performance. CB asks a question: how does the data pipeline work on the CS2 nodes? Is it also running on the CS2 processor, or is it running on CPUs? So let me go back to the slide deck here. So if you if we go back to Richard's slide at the beginning, similar to how we have these memory X and SWAM X, we also have workers associated with every CS2. These process the data loaders and feed samples to the CS2. And so that's why it comes in from the other side here. So you see samples and labels. So that's your input coming from the workers are being fed to the wafer. So the pipeline side is happening within the appliance, but is running on hardware outside of the wafer scale engine itself. Does that answer your question, Sibi? So as we can see here, the compile job started. CSETL, jobs. As you can see, we're now running both on the CS2.1 and CS2.2. So both systems has been queued up for this. If someone else was running a job ahead of time, we will just queue it up and it will wait in the queue state. But since no one else is running, we would be here, we're able to access both. Alfred asked the question, has just one giant wafer, is a distinction between CPU and GPU? So here in this specific example, we're actually going to be running on two wafers. So there are so ALCF has two systems or two wafer scale engines. And so this current model that we're running is going to be running on both of them, as you can see here, is being executed on 2 CSX, right? So that it is going to be executed on the actual hardware here on 2 of them in parallel. So we're not limited to only running on a single wafer. We can essentially linearly scale from 1 to 2 to 16 or even further. So there's no GPUs involved here at all. It's there are certain nodes associated with making sure we're feeding data fast enough for the wafer, because it's to make sure you get the best performance. And then the large part of the compute is essentially done on the wafer itself. There's no CPU or GPU on the wafer as such, Alfred. So if we go back to this deck, so these nodes that we have here, you can consider them as CPUs, and these are our actual wafers themselves. I'm not sure if you guys can see my mouse. So, but the things called CS2s are where the wafers live and where the compute is happening. And we have these memory X and SWAM X, which is our custom builds, which you can consider them as essentially CPUs.
Vishal, we had one more question in the chat from earlier that might have been buried. Can you work with the Cerebrus nodes remotely with VS Code, or do you have to be in the terminal?
You can use VS Code. So you can connect it. So VS Code allows you to have remote access where you can look at your code and make changes and things. So essentially, because you're running a Python script, you can run it the way you would run any Python script, essentially. You could even, in theory, spin up a Jupyter notebook and have your run script there and run it through that as well. For this example, since we're switching back and forth between the other tools and things, the terminal is comfortable. And even in VS Code, it provides a default. It has a terminal associated with it, where once you remote access, you can launch jobs from there as well. So you could launch this through the remote access once you're on this node, essentially, like how you would launch any other Python script. I'm not sure who asked that question, but great question. Hopefully that clarifies it. Thanks, Richard. And just like before, as you can see, same number of weights. And we finished sending the initial weights. We'll start seeing the training run soon. Let me kick off the tensor board in the meantime. As you can see, the second directory demo 2 shows up here. Obviously, no losses yet. Once it starts populating, we'll start seeing it here as well.
Vishal, as we're waiting for this, do you want to talk a little bit more about your background at Cerebrus? I know you're one of the more tenured folks here.
Sure. Yeah. I've been at Cerebrus now for about 5 years. I helped over this time. We worked very closely with ANL and Murli. I think Murli and I've been working together for 3-4 years almost. Since like our very first engagements.
That's right.
Yeah, so we go way back in that sense, for sure. And ANL has always been like a great partner for us, where we worked. During my time, I got to work on the Candle project that Andy mentioned yesterday. That was one of our earliest efforts. We got to do some very interesting things with ANL, where we were working with gravitational waves with another group. And then later on, we started working on some of the Stream AI MD that Andy mentioned yesterday as well, where we were able to augment simulation performance better using AI with one of our Cerebrus systems. And then last year, obviously, we helped with the Garden Bell effort as well. So we've done a lot of very, very interesting, very amazing work. Worked with a lot of amazing people at ANL. It's always been a pleasure, and it's been a great experience both for me and I think for the team as well. And as you can see, well, I can get back into all other cool things we got to do with ANL, but it looks like the losses are starting to show up. We can go over here and see what it's starting to look like. So like I mentioned, unfortunately, TensorBoard only updates every 30 seconds. So it tends to take a little bit of time before it shows up here. As you can see, and I'll show you quickly, but you can roughly see that based on the time steps and things, that the performance is roughly 2 times faster. And we'll show you in a bit on the TensorBoard as well that. So let's get the loss curve out. As you can see, especially if you remove the smoothing, the loss curves are essentially overlapping with each other. There is some slight difference. This is mainly because the way the data loaders are working here, where each data loader is feeding samples to a system. So the ordering is a little different between batches of data, but it's coming from the same source of data and doing the exact same model. And so you can see the loss curve is essentially overlapping with each other. And then as there's a little bit of a warm-up period beginning, but as we get towards closer to the end of the run, we'll be able to see the roughly 2x difference in performance as well. And yeah, but this is essentially all that's needed to go from like a 1 CS2 to a 2 CS2, or even an 8 CS2 or 16. You just essentially just say you want to use 2 systems, and you adjust your batch size so that it still fits rightly for your model and for the problem you're trying to solve. And that's all that's really needed. I think sorry, Alfred, could you clarify your question? I think the presentation and the recording will be available to everyone afterwards.
Since I joined a little late, I don't know what the steps that what do you type in? What the commands you type in the computer?
I see.
So yeah, it's good to have a record.
For sure. Yeah, maybe Maybe I can walk through it when we start the next demo as well. I can just kind of give a quick overview of the commands. They're very similar to get going. Or maybe once this run is done as well, I can show it before we go on break.
To add, Alfred, again, we'll also share the recording so you can also see that at your convenience.
Perfect. Yeah. So yeah, the recording, I'm assuming, will be available. So that should be good as well. But so as you can see, as we get towards the end, we're seeing the performance getting closer to about 1.1, whereas at the end here it's closer to 0.6. So we tend to see about the 2x speed up. And this behavior, the same trend is seen even as we get to larger models and as well as more clusters. So if you go from 2 to 8 or 16 systems, this linear scaling behavior is seen throughout. And as you can see on the loss curve, they tend to pretty much overlap because they are in essence running the exact same model.
Maybe a general question that may be of interest to many here. So when you're kind of looking at scaling from 1 to 2 CS2, so is the same steps, same approach that you kind of demoed now applies for any model as such?
Yes, this works for any model that we're running. There's nothing specific for running it on it, like running a GPT model, or later when I show the UNet model or any of that, we don't do, the scaling behavior of the system is the same irrespective of what type of model you're running. You're running a BERT or a GPT or any transformer model or even some of the CV models. As you can see here, and since there was a question earlier about the commands, so this is the command where I ran on the num CSX2. The only difference was this additional command. And if I go to the very first command, that's it. I just insert the default is one system. So the num CSX is set to 1, so I didn't specify it. And before we wrap up for the break, I thought I'll just quickly show the diff in the config as well, since in case.
There's a question on the chat on the executables on the disk or after the model compilation. Or they're just stored on the cache.
So the compile artifacts are not stored on the user node, it's stored within the appliance. But it is automatically used when you rerun the model the next time. So it does pick it up automatically. If it is a model you have run before, so depending on what the changes are, we almost have like a 2 tiers setup where if it's an identical model that you're running from before, we will just pick it up. If it's a small, depending on the level of change you've made, we may only compile certain parts of it because we know the rest of the artifacts can remain the same. And if it's a brand new model, then we would compile the whole thing. So just to show once again, the difference between the two configs is fairly straightforward.
A related question: Did we see any compiles in the 2 demos that you did?
So yes, so all these models, so that it'll always launch a compile job. So if I go above here, you can see compile successfully written.
Yeah.
So we will always do a compile job. Underneath, it really depends on if someone else has run this model before, or it does depend on the user. So if you've run the model yourself before, in this case, I think these models have been run before. So they were essentially, only took a few seconds to go through. But even if it's not run, we're usually talking, on the order of minutes for it to go through. So as I mentioned here, the only difference here is the batch size we changed. This is just so that when the batch size specified here is per system. And so since we're running on 2 systems, we have the global batch size remaining at 120. In a future release, we are changing this so that you only specify the global batch size throughout, and the systems will handle the sharding of that as well. So you wouldn't even need to make this change in an upcoming release. But that's basically the only difference from going from 1 to n systems, is you just choose how many systems you want to go with. I think
Hi, Vishal. I think one interesting thing for the users to see would be the compile artifacts, like how they look and what all they contain. So do you think you can share some information regarding that?
So the compile artifacts goes through various stages from the PyTorch code through our compiler stack. It goes fairly in detail, and it doesn't, it essentially goes through like very specific Cerebrus specific things. On the high level, we're built on top of the MLIR stack in terms of our graph lowering. But then it goes into the specifics of, different layers of different purposes. And then we essentially, at a high level, you can think of it as we take the operations at the PyTorch, we lower it and map it to the right kernels, and then we essentially handle the distribution and sharding of it across the systems and the resources. And then that gets packaged into what you can think of as an executable, which then gets executed. I don't think there's a way for you to actually see those artifacts here, because I think those are stored within the appliance itself.
Okay, thanks.
Yeah. So these were the first two demos. So, as I mentioned, it's the same system architecture. The execution is exactly the same. And, we don't change any behavior or how we run things when we're going from 1 to 2. There's no new code that needs to be written to go from 1 to n systems. It's as simple as just changing how many systems you want, and the rest is essentially handled by the software.